Welcome back to the lectures on chemistry on the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. We will continue with the lecture on the interaction between two spin-half systems, quantum chemistry. A little bit on my personal, on a personal note. Actually, I want to thank one of the great teachers I've ever had in my life who taught me angular momentum and who taught many things about the coupling between angular momenta and the whole of the theory of NMR spectroscopy. And it's extremely important that sometime during these lectures I mentioned that I learned from some of these great people, and the first and foremost among them is Professor Brian Sanctuary, McGill University. He was my PhD mentor during the period 1982 to 1987. This is one of the most famous universities in Canada and all over the world. It's in Montreal, Canada. And another extremely important and one of the most influential professors in the academic value system that I have learned is also Professor Robert Snyder, with whom I spent the first postdoctoral period in the University of British Columbia. This is on the other side of Canada, namely in Vancouver, one of the most beautiful cities in the world. And thirdly, in these areas, particularly in the areas of angular momentum, the third and an equally important learning that has happened to me is through my association with Professor Tucker Carrington Jr. His father is also Tucker Carrington, and he was a professor. He was earlier a professor of physical chemistry in the University of York. But Professor Tucker Carrington, when I was associated with him as a postdoctoral fellow, PDF, so I should write junior. He was in the University of Montreal. Currently, he is now a chair professor in the Queen's University, Kingston, Canada. I mean, many years ago, but these are three professors from whom I should say I have learned the most of angular momentum, both from the point of view of magnetic resonance, where we use the convention that the angular momentum commutation relations have a plus IH bar on the right hand side, namely the IX, IY commutator is plus IH bar IZ. That's what we do in all of magnetic resonance and all of the electronic spectroscopy. And then the moment you go to molecular spectroscopy and you look at rotational angular momentum and the coupling of angular momentum with vibrational motion and all the others, the sign changes due to the anomalous computation relations and due to the fact that we use a molecule fixed coordinate system. So angular momentum from both the body fixed axis as well as the space fixed axis. I mean, I learned a lot of these things from all the three professors, so it's important for me to remember, at least at some point of time, that there were great people who taught me. Of course, whatever the mistakes I make are mine. Okay? That is also known. Let us start with two spin-half systems. Not two independent spin-half systems. So I would write two spin one half system. The spin one halves are coupled to each other or interact with each other. An angular momentum being a vector, if we assume that the spin 1 has an angular momentum I1, we are removing the h bar out of the picture because this is a dimensionless angular momentum. At any point of time, we can always bring it back to the measured quantities by putting in the right dimensions. One spin with I1 and another with I2, and the total angular momentum associated with the two spin system is I1 plus I2. It's a vector addition. Therefore, the total angular momentum square, which we will call as I, the total angular momentum squared, I squared is I dotted with I, and the equation is I1 plus I2 dotted with I1 plus I2, which when you expand gives you I1 squared plus I2 squared plus 2 I1 dotted I2. Remember, spins 1 and 2 are dynamically independent. Independent in the sense the operators associated with these two spins, this is what it is, operators associated with two spins are independent of each other. Therefore, the first thing we have to know is that the operator for spin 1, which contains I1x, I1y, I1z, these are the x component of spin 1, y component of spin 1 and z component of spin 1. They are related to each other, they do not commute among themselves. However, I1x commutes independently with I2x, I2y, I2z. Okay. The commutator, if you take this, the commutator of I1x with I2x or I2y or I2z, they are all 0. And likewise for, if you replace x by I1y, and with the corresponding these three quantities that you have, corresponding quantities with I2x, I2y, I2z. All these commutators are 0. And similarly for I1z with I2x. However, the commutator of I1x and I1y, they have the same relationship that we have studied till now in the last 2 or 3 lectures we have seen. So, this is what is called the dynamical independence of the operators associated with independent particles. Okay. We will keep this in mind. The moment we have 2 spin 1 halves I1 and I2 interact with each other, then what is the state of the 2 spin system? You had already some indication of a joint probability or a joint wave function, and now you have to go back to the first exercise in the model problems of quantum mechanics that we did, namely the particle in a one-dimensional box and the particle in a two-dimensional box. If you recall the particle in a two-dimensional box, we considered the motion in a plane, but the x and y coordinates were independent of each other, and since there was no potential of interaction between the two particles in that system, except that they both were confined to infinite boundaries, potential boundaries, you recall that we wrote the overall wave function of the two particle system as the x component, the overall wave function for the two-dimensional, the particle in a box system x and y, as the product of the two one-dimensional systems, the x component only and the y component only. In a similar way, if we talk about two independent particles, the joint probability or the joint wave function associated with this is the direct product. It's called direct product. I'll explain that in a minute, okay, of the wave functions of the two independent particles. Of particles 1 and 2. So, let us start with a spin a half system to begin with, because that is easy. The rest is algebraically more complicated, but not the principle. So, let us take spin a half, two spin a half systems. So, we have what is called I1x, I1y, I1z, and I2x, I2y, and I2z. Then we have I1 square, I2 square, and then we also have I squared, which is I1 square plus I2 square plus I dot 1 dot I2 times 2. Okay. And then we can also write the Iz as the sum of the two z components of the two individual spins I2z. So, we will need to look at the effect of some of these things in our analysis of two spin a half system. What are the basis functions? For spin 1, I1, we wrote down alpha 1 and beta 1. For spin I2, spin a half system, both I1 and I2. We have alpha 2 and beta 2. The 2 corresponds to or denotes the spin 2 state, and the 1 subscript corresponds to spin 1 state. The joint product basis now contains alpha 1 and any one of these, alpha 2, alpha 1, beta 2, and likewise beta 1, alpha 2, and beta 1, beta 2. Therefore, we have 4 basis functions. Why it's called a direct product? The total number of basis functions we have is 4 compared to the total number of basis functions that we have for a spin 1, which is 2, and spin 2, which is also 2. And if you write the matrix representation, please remember alpha 1 corresponded to the matrix 1 by column vector 1 by 1, 0, and beta 1 corresponded to the column matrix or column vector 0, 1. Alpha 2 is also represented as 1, 0 in 2 dimension as a single spin system, and beta 2 is 0, 1. However, the joint state of the 2 spin system alpha 1 alpha 2 is the direct product of the 2 column vectors, and the direct product will now give you, this is a 2 by 1, this is a 2 by 1, the direct product gives you 4 by 1. It's a column vector 1, 0, 0, 0. And likewise, the state alpha 1 beta 2 is the direct product in matrix representation of the 1, 0 and 0, 1, which is 0, 1, 0, 0. And you can see immediately the state beta 1 alpha 2 is going to be 0, 0, 1, 0, and beta 1 beta 2 is the matrix 0, 0, 0, 1. So, the 4 by 4 matrix representation for 4 by 4 matrix representation for the 2 spin operators, they follow. So, you have 4 states alpha 1 alpha 2 given by the column 1, 0, 0, alpha 1 beta 2 given by the column 0 1 0 0, beta 1 alpha 2 given by this 0 0 1 0, and beta 1 beta 2 given by 0 0 0 1. Okay. These are the 4 states for a 2 spin-a-half system. Therefore, all operators for the 2 spin-a-half systems will have 4 by 4 matrix representation. Very quickly we can see this. I1 plus. Now, if you think about I1 plus on alpha 1 beta alpha 2, it is 0. I1 plus on beta 1 alpha 2 is going to give you alpha 1 alpha 2. I1 plus on alpha 1 beta 2 is also 0, and I1 plus on beta 1 beta 2 will give you alpha 1 beta 2. Okay. Therefore, what you see here is that the representation for I1 plus in a matrix form will be now 4 states: alpha 1 alpha 2, alpha 1 beta 2, beta 1 alpha 2, and beta 1 beta 2. And the same thing here on this side: alpha 1 alpha 2, alpha 1 beta 2, beta 1 alpha 2, and beta 1 beta 2. Okay. This is I1 plus is 0. I1 plus on alpha 1 is also 0. I1 plus on beta 1 will give you alpha 1 alpha 2, therefore this is 1. I1 plus on beta 1 beta 2 will give you alpha 1 beta 2, and that is not the same thing, but this is 0. And likewise, all these things, I1 plus on all these are alpha 1 alpha 2 states, so all 4 of them are zeros. Okay. We have to only look at this one. This is alpha 1 beta 2, therefore here you have alpha 2, therefore it is 0, because I1 plus will not change the second spin-a-half state. It will beta 2, therefore this will be 1. And the rest of it is also 0, because this is a beta state, the betas will be changed to alpha, this will all be 0. Okay. So this is a way of writing down the matrix element representations, matrix representations for operators. Of course, you have got 3 operators, one x, one y, one z, or 1 plus, 1 minus, and 1 z, whichever it is. So you have 3 operators on for the spin 1 and 3 operators for a spin 2, and therefore you have essentially 9 such product operators. But if you calculate for a spin-a-half, including the identity, which is the 4th operator, there are 16 operators, and 16 operators will be represented by these 4 by 4 matrix representation in some way. This is the idea of what is known as a direct product. But let's get to the simple interaction between the 2 spin-a-half systems, namely the total angular momentum I given as the sum of the 2 angular momenta I2. Therefore, let us first look at I square, which is I1 square plus I2 square plus 2 I1 dot I2. Now, the I1 dot I2 can be represented by the corresponding plus minus operators. So, you can write this as I1x, I1 I2x plus I1y, I2y plus I1z, I2z. And this can be changed to plus minus operators. So, it is a very elementary algebra for you to verify that this gives you 1 by 2 I1 plus I2 minus plus I1 minus I2 plus I1z, I2z. quick hint, I1 x is 1 by 2 I1 plus plus I1 minus, and I1 y is minus I by 2 I1 plus minus I1 minus, and similarly for spin 2. Use that substitution to get this form. Therefore, the operator I1 dot I2 now contains the raising operator for spin 1 and the lowering operator for spin 2, as well as the lowering operator for spin 1 and the raising operator for spin 2. I1z and I2z of course act on the eigenfunctions and they do not change the eigenfunctions, but the raising and lowering operators will change the eigenfunctions of alpha 1, alpha 2 or alpha 1 beta to something else, and therefore you have to watch that the operator I1 dot I2, these are not probably the suitable basis functions, these 4 basis functions that you have. They are not eigenfunctions of this operator. Also, if you look at it, the Iz, which is the z component of the total angular momentum, I square, the z component is I1z plus I2z. And this needs to be calculated for the alpha 1, alpha 2, all the 4 states, and you can calculate that. So, we have 2 sets of operators, namely I1 square, I1z, which were used to define the states alpha and beta, and I2 square, I2z, which were used to define the alpha beta states of spin 2. This is one set of operators and the corresponding eigenfunctions alpha 1, alpha 2, alpha 1, beta 2, beta 1, alpha 2, and beta 1, beta 2. On the other hand, the coupling between the two gives you again the spin 1 I1 square and spin 2 I2 square, but now it gives you I square and it gives you Iz. So, these are the 4 operators for which we may need to find eigenfunctions using the properties of the operation of these operators on these functions. So, this is called coupled basis and this is called the product basis. Okay. So, I will indicate the first couple of steps and then the rest of it can be derived in the same way. Let us look at the I square on alpha 1, alpha 2. Okay. I square on alpha 1, alpha 2 is I1 square on alpha 1, alpha 2 plus I2 square on alpha 1, alpha 2 plus 2 times I1 dot I2. So, there is already a 1 by 2. So, what you will have is I1 plus I2 minus plus I1 minus I2 plus 2 times I1z, I2z acting on the state alpha 1, alpha 2. I1 square will give you 3 by 4 on alpha 1 and alpha 2. I2 square on alpha 2 also gives you 3 by 4 and the state back alpha 1, alpha 2. And you can easily see that I1 plus acting on alpha 1 is 0. Therefore, it gives you the first term is 0 and I1, I2 plus acting on alpha 2, that is also 0. Therefore, the second term acting on the state gives you 0, but the third term acting on the state alpha 1, alpha 2 is the product of I1z acting on alpha 1 and I2z acting on alpha 2, and each one gives you a half. Therefore, it is 1 by 4, but the sum is 1 by 2 because there is a 2 here and it also gives you alpha 1, alpha 2. So, the answer here is 2 times alpha 1, alpha 2. Therefore, the state alpha 1, alpha 2 is an eigenfunction of I square. No problem. What about beta 1, beta 2? It's easy to verify this on I square. You will get exactly the same thing 2 times beta 1, beta 2. I leave it to you as an exercise to do the same way that you have done the other one. However, I square on alpha 1 beta 2 is quite interesting, and you will see it right away that it is not, alpha 1 beta 2 is not an eigenfunction of I square. So, it is I 1 square acting on alpha 1 beta 2 plus I 2 square acting on alpha 1 beta 2 plus I 1 plus I 2 minus plus I 1 minus I 2 plus 2 I 1 z I 2 z acting on alpha 1 beta 2. This is of course I 1 square on alpha 1 gives you the same things, therefore, you have 3 by 4 alpha 1 beta 2, and you have also 3 by 4 acting on alpha 1 beta 2. But now, the first term I 1 plus acting on alpha 1 is going to be 0, therefore, this is 0. However, the second term, which is I 1 minus I 2 plus, you can see that I 1 minus acting on alpha 1 gives you beta 1, it brings the state down, and I 2 plus acting on beta 2 gives you alpha 2, and therefore, you can see that the product of this is going to give you beta 1 alpha 2. And then you have the 2 I 1 z I 2 z acting on alpha 1. Remember, I 1 z on alpha 1 gives you half, and I 2 z on beta 2 gives you minus a half. Therefore, the product is minus 1 by 4 times 2 is minus a half. So, what you will have is minus 1 by 2 alpha 1 beta 2. Okay. So, you can see what you get. You get the state alpha 1 beta 2, 3 by 4 plus 3 by 4 minus 1 by 2. These three states you can put them together. 3 by 4 alpha 1 beta 2, 3 by 4 alpha 1 beta 2 minus 1 by 2 alpha 1 beta 2. That gives you simply alpha 1 beta 2. Okay. But the other state is beta 1 alpha 2. Therefore, you see I square on alpha 1 beta 2 gives you that. So, this is obviously not an eigenfunction of I square. It gives you the product of two states, and likewise do exactly the same thing. I square on beta 1 alpha 2 will give you the same thing, namely alpha 1 beta 2 plus beta 1 alpha 2. Okay. So, it is quite clear that I square on alpha 1 beta 2 plus beta 1 alpha 2 gives you twice, because it gives you once for this and the same thing for the other. Therefore, it gives you twice alpha 1 beta 2 plus beta 1 alpha 2. Okay. So, the state alpha 1 beta 2 plus beta 1 alpha 2, which is the sum of two spin states, that is an eigenfunction of the total angular momentum I square, the square of the angular momentum I square with the eigenvalue 2. So, you have got three functions, namely alpha 1 alpha 2, that is if an eigenfunction of I square giving you 2 alpha 1 alpha 2. I square on beta 1 beta 2 is also an eigenfunction with the eigenvalue, same eigenvalue beta 1 beta 2, and the third one I square on alpha 1 beta 2 plus beta 1 alpha 2 is also an eigenfunction of the I square operator alpha 1 beta 2 plus beta 1 alpha 2. So, you have got three functions out of the four, one being a linear combination of two of them, all giving you an eigenvalue 2. What about Iz on these three functions? Iz is I1z plus I2z. I1z plus I2z acting on alpha 1, alpha 2 will give you I1z on alpha 1 is a half and I2z on alpha 2 is a half, and the states will be the same. So, it is half plus a half on alpha 1, alpha 2. Therefore, this is 1 times alpha 1, alpha 2. Okay. And likewise, I1z plus I2z on alpha 1, sorry, on beta 1, beta 2 will give you, this will give you a minus a half, this will also give you a minus a half. So, you will get minus 1 times beta 1, beta 2. And it is easy for you to verify that I1z plus I2z on this combination states of alpha 1, beta 2 plus beta 1, alpha 2. If you do that, you can see that, let us take the first one. I1z on alpha 1 will give you plus a half, I2z on beta 2 will give you a minus a half. It is a sum, therefore, the product, the sum is 0. And likewise, I1z on beta 1 gives you minus a half times the same states, and this gives you a plus a half times the same states, therefore, this gives you 0. So, what you have is, there are three states which have a total angular momentum value I is equal to I square is equal to 2, and the total angular momentum z component having 1, 0 and minus 1. This corresponds to, of course, the quantum number I is 1. I square gives you an eigenvalue 2, but the quantum number is I into I plus 1, and therefore, this is a spin 1. Okay. There are three states, the alpha 1, alpha 2, beta 1, beta 2 and this combination. These three states form a spin 1 system in which the total angular momentum is given by the square, namely I into I plus 1, and the component of the z angular momentum operator, total angular momentum operator, z component has three values 1, 0 and minus 1. Therefore, this is called a spin 1 state. You will also find out that there is only one more state, namely alpha 1 beta 2 minus beta 1 alpha 2. If you take this state and you calculate the effect of I square or I z on this, you will see that the answer you get is 0. And just to see this for I square on the state. You know that I square on alpha 1 beta 2 gives you 2 times alpha 1, sorry, it gives you not 2 times, it gives you this combination alpha 1 beta 2 plus beta 1 alpha 2. And you also know that I square on beta 1 alpha 2 gives you the same thing. Therefore, if you take the difference between the two states, beta 1 alpha 2, of course, these two will cancel each other and you will get 0. And the same thing like this, Iz on these, you can see that Iz is I1z plus I2z on alpha 1 beta 2 anyway gives you 0, and it also gives you 0. Therefore, Iz acting on the state is 0. Therefore, you have a state which is an eigenfunction of the I square operator with I equal to 0 and Iz operator with also the m equal to 0. Therefore, this is called the 0 spin state. Okay. So, let me summarize that if you have I1 square, I2 square, I1z, I2z, then the four operators that you have, the product operators, they are all eigenfunctions. So, let me write them in a tabular form for you. Let me write alpha 1, alpha 2, I1 square will give you 3 by 4, alpha 1 beta 2, I1 square will also give you 3 by 4, and then you have beta 1 alpha 2 and beta 1 beta 2. So, all of these will be 3 by 4 and this is 3 by 4, 3 by 4, 3 by 4 and 3 by 4. And the I1z on this state gives you 1, I1z on this state gives you again 1 half, and I1z on the beta state gives you minus 1/2, and I1z on the beta 1, beta 2 state gives you minus 1/2, and this will be I2z acting on alpha 2 gives you plus 1/2, I2z acting on beta 2 gives you minus 1/2, I2z acting on alpha 2 gives you plus 1/2, and I2z acting on beta 2 gives you minus 1/2. Therefore, all these are eigenfunctions of these 4 operators. The eigenfunctions for the 4 operators that we have, I1 square, I2 square, I square, and Iz. If we do this, you will see that alpha 1, alpha 2, alpha 1, beta 2 plus beta 1, alpha 2, then beta 1, beta 2, and the state alpha 1, alpha beta 2 minus beta 1, alpha 2. If you take these, I1 square gives you 3/4. I1 square on this gives you, you can see that 3/4 plus 3/4, but this is a sum, so this will also be 3/4. I1 square on this gives you 3/4, and I1 square here gives 3/4. I2 square, 3/4, 3/4, 3/4, and 3/4. I square on the state gives you twice the state, I square on this gives you twice the state, and I square on this gives you twice, and I square on the state gives you 0. And the Iz on alpha 1 gives you 1, the state, the Iz on the state gives you 0, Iz on the state gives you minus 1 times the state, and Iz on the state gives you 0. Therefore, you see that these 4 are eigenfunctions of these 4 operators. And this contains the sum of the angular momenta, both the components as well as the total angular momenta, and therefore, this is called the coupled basis. One last statement, these states have to be normalized, and since these states are orthogonal to each other, the normalization simply means that the state is now 1/√2 alpha 1 beta 2 plus beta 1 alpha 2. That is a normalized state, and the state 1/√2 alpha 1 beta 2 minus beta 1 alpha 2 is also a normalized state. Therefore, we have the labels now. We have the labels, namely IM labels corresponding to 1, 1, 1, 0, 1 minus 1. If you do that, these states are alpha 1 alpha 2, 1/√2 alpha 1 beta 2 plus beta 1 alpha 2, and the other state is beta 1 beta 2. Okay. And IM 0, 0 state is 1/√2 alpha 1 beta 2 minus beta 1 alpha 2. It's that. So, these are the IM states, and here you have I1 M1, I2 M2. Okay. So, these are the product states, the 4 of them, alpha 1, alpha 2, alpha 1, beta 2, beta 1, alpha 2, beta 1, beta 2. So, these 4 states are obviously taken as a linear combination here to give you what is called the coupled states. These are the product states. And the coupled states are labeled by this quantum number. Let me write that, highlight this. These are the coupled product basis states. Now, if we write this as a matrix element or as a matrix relation, you have the following, namely 1, 1, 1, 0, 1 minus 1, and 0, 0. If you write this as a column and you write the matrix of coefficients with the states alpha 1, alpha 2, which is the product, alpha 1, beta 2, beta 1, alpha 2, and beta 1, beta 2. If you write that, then you can see immediately that the state 1, 1 is the same as that state, therefore, the coefficient here is 1, 0, 0, 0, because 1, 1 is not connected to any other. The state 1, 0 is a linear combination of these two states, and therefore, and it's 1 by root 2, 1 by root 2 and 0. The state 1 minus 1, you can see that from this relation, 1 by root 2, 1 by root 2 is the state 1, 0. And 1 minus 1 is connected only to that, therefore, that is this. And 0, 0 is a linear combination with a negative sign between them. So, this is 1 by root 2 and minus 1 by root 2 and 0. What is this matrix? This matrix is known as the Clebsch-Gordan coefficient matrix. Clebsch-Gordan coefficient matrix. Which connects product states to coupled states. We will see what its impact is in the electron coupling between the two electrons, and the fundamental principle that was first stated by Wolfgang Pauli as the principle of antisymmetry, and the antisymmetric Pauli's antisymmetric principle for antisymmetry, or when the two electrons are exchanged, will have this, whatever we have done will have a strong implications on that. In the next lecture, we will connect this to the actual electron states and also what is called the singlet and the triplet states that you are familiar with in quantum chemistry from elementary spectroscopy. These are essentially what are called the singlet and the triplet states, the 0, 0 state. This is called the singlet state, and is the most famous one in quantum mechanics, and first it was used by Wolfgang Pauli. It was predicted to have a 0 spin, and it's called the antisymmetric state when the two electron spins are interchanged, and the other three states are called the triplet states. We will see more of that in the next lecture. Until then, thank you very much.